Hello everyone, welcome to Class 1 Fundamentals and the Principles of NDT. Today we'll start the week 2. In this week, we'll talk about elasticity and the linear fracture mechanics. The learning objectives of this lecture including understand the basic concepts and terms of the elasticity, and to provide enough background to linear elastic fracture mechanics. First, let's discuss about the stress. Stress is the very basic concept of how material responds to external load. And the stress, by definition, equal to force per unit area, or F divided by A, force over the area. So there's a couple different type of the force. The one type we are often use is normal stress. Normal stress is the force perpendicular to the areas per unit area as been showing on the schematics on the left. As you can see, the force is applied perpendicular to the face of these objects on the x, y, and the z directions. And if the force applied, which is the parallel to the area per unit area as been showing on the right, that's what we call the shear stress. Let's start by recap the sign convention for normal and the shear stress. For normal stress, there are two types. One is tension, or we call extension. In this case, as shown here, you have a force pulling the materials outwards as been shown here. So this is a positive. In contrast, if we try to pull material inward, we call it a compression, which is negative force. On shear stress, first you have to define the positive phase. Those with normals in position XYZ direction. For instance, in this case, I define X direction here, which is positive X direction. So Y direction here is a positive. So in this case, the shear stress, tau XY in X direction is positive. In Y positive direction is positive. So therefore, positive shears acts in the positive direction on the positive face or acts in the negative direction on the negative face. So if my shear stress on positive XY, it means the X in this direction is a positive. So vice versa, the negative shear stress will be on the negative X. So going to this direction, that will be the negative. And then the Y is going downwards. That's the Y. So the positive shear acts in the positive direction on the positive face, or acts in the negative direction on the negative face. So we have two things, is the direction and then the face. As we apply the stress, the material will deform. The amount of the deformation per unit original length is quantified as strain. For normal stress, we will induce normal strain. The normal strain is described as Greek letter epsilon. Epsilon equal to the total length after the deformation minus original length equal to delta L divided by original length. On the other hand, for the shear strain, which is tangent gamma equal to delta L over the L null. So therefore, gamma equal to, for very small gamma, and then the gamma equal to delta L over the L. So basically is the deformation, the delta over original length. First, let's recall the concept of uniaxial tensile testing. Uniaxial tensile testing is to apply uniaxial tensile load along the x-axis of the testing sample as been showing here in this dog bone testing coupon. As we see, when we apply a load P, we extended the length of this original dog coupon from 5 centimeter to 6.5 centimeter. So therefore, the tensile stress sigma equal to P over the area A naught epsilon, the strain equal to Y divided by LO, which is the strain. So therefore, we can get this stress strain curve as been showing here. So first is the linear deformation area, which is about 0.2% of the strain in general. So as been showing here, when the material have around the 0.2% of the strain, and then we can see a very linear behavior of the material. That means the sigma, the increase of the sigma is linearly proportional to the increase of the epsilon. And the tangent of this curve, which is E again is Young's modulus, or modulus of elasticity, which is intrinsic material property. Again, E equal to sigma over epsilon. Again, this is intrinsic material property. When we say intrinsic, it means this is not dependent on sample geometry. It's not dependent on the sample size. What is really dependent on is material itself. In other words, we will expect steel has very different Young's modulus with polymer or with concrete or with wood. But if we keep the same recipe of the steel or keep the same recipe of making the concrete, we can expecting a same Young's modulus. It really doesn't depend on the sample size or the sample length. Now let's quickly recap the testing procedure of the uniaxial tensile test. So first you have a material with original length as been shown here. And then we apply a tensile stress, which is extended length outwards. And the force is P. And then the stress will be equal to P over A naught, the area of the force has been applied. And that force will generate or will induce a deformation. Again, the deformation over original length L naught equal to the strain epsilon. Again, let's define the conventions. So you have x direction going this way, and then this is y direction, and then this is a z direction. So in this case, the sigma, the tensile stress should be equal to the stress applied on the x direction. So as such, on the y direction, the z direction, and the shear, they all equal to 0. So there is no shear force or there is no any force applied in other direction. So as such, we will expect the deformation generated or the strain epsilon x will be epsilon. So the total deformation of the material will only be the deformation in the x direction. And also x. However, the epsilon y and the epsilon z are not equal to 0 because when this material, as expected, when the material is going longer in this direction, it will become thinner in this direction. However, since there is no shear stress, so therefore gamma xy, gamma zy, and gamma xz should equal to 0. So in this case, we can draw stress over strain curve or sigma over epsilon as we have been showing. We're expecting the very linear behavior at the very beginning. And again, this deformation over the sigma over epsilon is modulus. As been showing here, and we have seen the material has very linear behavior. That means with the increase of the stress, the strain increase has been linearly. However, quickly we will notice once we keep the stress at the same time, however, we will develop a substantial strain as been showing in this area. We have very small the stress increase, but we have a substantial strain development. And that strain development will continue going. Again, in this case, the epsilon, the deformation will develop not only in x direction, but also in y and z direction. However, there is no shear stress or shear strain. So for uniaxial tensile test, again, it's important to understand we will apply a tensile load, which is outwards to extend the materials. And the displacement is measured as a function of the loading. So therefore, for testing for NDT, its most important case, the testing machine apply a displacement. In other cases, it control the loading. So it depends on what type of the testing setup. Sometimes it's control the deformation, then sometimes it's control the loading. So we need to measure the load by using a load cell. And for deformation, we can use a strain gauge or extensometer has been showing here. Or currently there is newly developed methods such as using a laser or optics, for instance, a digital image correlation DIC, which have a better or more accurate measurement. To describe material property, in this case, I will use high strength steel as example, as been showing here in the figure here. You could describe material property as the load versus deformation, or you could describe material by using stress over strain curve. As we have been showing, both curve has very similar trend or the relatively identical shape. What is really interesting is in this area. So if we magnify that area, we would see we have very linear behavior at about 0.2 deformation. And if we focus on this area, as we have been showing, actually, under the stress, the strain will get very, very small. So we have very small linear behavior area, which is induce a very large stress, induce a very small strain. And the rest of this area will be nonlinear. So again, the Young's modulus is the tangent of this curve. That's the intrinsic material property. So it's never good to use the stress or strain to describe a material. Why? Because that's not intrinsic material property. That it really depends on the material geometry. So therefore, for uniaxial tensile testing, we can get the sigma equal to a function of the strain. And that function actually is linear function at the linear behavior, which is Young's modulus. Again, the modulus of elasticity. For nonlinear behavior, we will talk in the next couple weeks. For most of the material, we will expect that their stress strain curve has been showing as here, which includes two material behavior. First, we call it elastic behavior, which has been showing on the left. As you can see, the increase of the stress will induce the linearly increased strain. And that relationship d sigma over d epsilon equal to modulus of elasticity or Young's modulus. Once we pass the linear region, we will expect the substantial increase of the strain induced by incremental increase of the stress, and then the stress will reduce and continuous increase of the strain. In this area, we call plastic behavior. We will discuss the plastic behavior in the next week. Again, so let's quickly recap what we learned in this class. We talk about uniaxial tensile stress testing. The tensile stress, sigma equal to this force over the area. The strain epsilon equal to the delta L over L null, the regional length. So we discussed the stress and the strain curve, which we see this is a very important material property that can present lots of behavior as being shown here. Look at this red curve. The stress strain curve will tell us a lot of information. The first information we have spent quite a bit of the time to discuss is called E, Young's modulus, modulus of elasticity, that also describe the stiffness of the material. That is the material property to describe the material's ability to resist the deformation. Of course, E is higher, it means the less deformation at the same amount of the stress applied. There's a couple points are very important. In first points here, at the turning point from the linear behavior or elastic behavior to plastic behavior, this we call it strength of yield or sigma yield, which is the stress of the yield, and Sy it means the strength of the yield, how strong the material before it's yielding. And this is the ultimate stress of the material or ultimate strain of the material. How strong of the material become a failure. And this is a fracture, which we will talk in the next class. Fracture means material will break into multiple pieces. So this is the strength of the material before its failure. So the area under this curve, it's called the toughness. It's describe how tough the material is. So by conducting uniaxial tensile testing and plot the stress strain curve, we can expect the material's behavior differently under different stress and strain. And therefore, we can understand the material property just by looking at this simple stress strain curve, sigma over epsilon. For instance, if I have a steel, and this is a typical behavior I would expect for a normal steel. But if I would increase the strength of the material, so therefore, I would expect the stiffness of the material will increase, the modulus of the increase. As you can see here, the slope of the blue curve is way higher than the red curve. So as such, the material will present the very high stiffness, the high strength, however, a lower toughness because of the area under this curve has drastically reduced, such as the carbon fiber. Still, as been showing here, the tension failure of the brittle material, as we can see, is very nice fracture surface, very clean, and then all of a sudden break into the two pieces. On the other hand, I could lower the stiffness, lower the strength, and get okay toughness. For instance, in this case, this may be aluminum. So if I have a piece of aluminum material, I have the same shape with the carbon fiber still, and when I'm doing the uniaxial tensile testing, I would expecting it will start to develop a neck area, and then eventually will fill. And then as you can be seeing here, the deformation of the sample has been substantial. Rather, in contrast, there is the very, very small or marginal deformation. So in summary, in this lecture, we have talked about very basic concept, stress and strain, and we reviewed the normal stress and shear stress. And then we discussed the stress strain curve, and we talk about the modulus of the material and the toughness of the material, and how can we use the stress strain curve to understand the material property. So the coming next, we will further discuss elasticity.